Hey class, Adam Ward here. Want to talk to you about an advanced topic on how pulse and slug injections are related, convolution and its inverse, the deconvolution. So the big question here perhaps is, why is it that some people are getting the exact same information when they do a pulse injection or a constant rate injection? Well, in a perfect system, we can either combine or take back apart the signal. Let me show you what I mean. So let's think of a pulse injection where our input to the study reach, so what we've put in at the upstream end would be sort of a pile of 4 blocks. And we could think of it as traveling down some conveyor belt through a black box, and on the other end, what comes out is those same 4 blocks, but they've been rearranged. So there's some delay in time, that's why they're shifted to the right, but there's also some characteristic change in shape, where instead of a pile of 4 blocks, one has moved left and one has moved right. And so you can imagine each time you put a pulse into that system or a stack of 4 blocks onto the conveyor belt, they come out the other end looking the exact same way. What you've just found is the characteristic way that an input signal, 4 blocks stacked up, gets translated into an output signal, this sort of 3 wide with 1 extra in the middle. And so a constant rate injection in this world is going to be nothing more than a series of pulses that are all overlapping with and adding up to one another. So that very first input should look just like our output. But in a constant rate, we follow that immediately with another input. Perhaps it's 4 red blocks this time. And so I've drawn those 4 red blocks up above. And then what I want you to imagine is this is like a game of Tetris almost, and those 4 blocks are going to fall down and they're going to stack up on top of the blue or add to the blue signal. So that first block with the stripes would fall there. The middle 2 with the polka dots would fall there. And the third block with the hatching going the other way would fall to the right. So now we've put in a blue signal and a red signal, and we can see that they're interacting with one another. They're starting to overlap a bit. If we continue this with pink, yellow, and green and purple blocks, what you start to see is this pattern emerge, right? The constant rate can be represented as a series of pulses, one after the other. And the downstream signal that you measure is the piling up or the stacking up of all of those pulses. So this is our constant rate injection on the left, our downstream observation on the right, and when that starts to hit that steady flat portion labeled as plateau, that's when we know we've brought our stream up to a steady state. That was the goal of our injection. So the process by which we take these independent signals and combine them to get the more complex signal on the right is the process of convolution. For our purposes, you could think of this as the adding up and the mixing together of multiple input signals. Now, if we had that downstream observation, can we recover what the characteristic transformation would be? We absolutely can, and that's a process called deconvolution, or taking this complicated signal and splitting it back apart into what the equivalent transformation would be at the top, shown at the top of the screen. So in this course, we're not going to go into deconvolution, but in the resources that go along with this learning activity, I'll put some resources where you can dive deeper into the process of deconvolution for stream solute tracers if you so choose. But this idea of convolving and deconvolving, this is why we think that pulse injections and constant rate injections ought to give us the same information. In a perfect system with perfect tracers, that would be absolutely true. Thanks, everybody.